Hey, good afternoon, everyone. Any questions about either one of the labs? Okay, so question? No? Yes?
It's not about the labs themselves, but so the lab is due on Sunday. Do you have to demo before the due date?
No, it's based on when you submit. So you can demo afterwards. So we'll enter your grade after you demo,
Okay.
but we'll base the submission time on when you uploaded.
So I could submit it on like Friday and demo it the following Wednesday without any grade time?
That's right.
Okay.
That's right. Yeah.
I do have a question.
Yes.
Yeah, the instructions say to, after you've compiled everything, to simulate Testbench.
Mm-hmm.
But is Testbench actually the one that we created?
Yes.
So it'll be SimTop or whatever we call the top?
Right. Well, you'll put it in SimTop, but I'll talk more about that today. Okay, so hopefully all of you were in one of the lab sessions last week, but I'll briefly review the material I covered in there. So I was talking about SystemVerilog. So we have an example module where we have 4 single-bit inputs and one 1-bit single-bit output. And inside the module, we assign the output to be a Boolean logic of the inputs using a continuous assignment statement. And as I mentioned, the way this works is anytime any of the signals on the right-hand side of the assignment statement change, it activates the assignment statement and updates the value that sets, updates y. So here's an example of simulating that, where we take the 3 inputs and go through every possible permutation of those using a counting sequence from 0 to 7, effectively, because there's 3 bits, A, B, and C, so you can treat those like 3 bits of a number. And then this is what you get after you synthesize it. We talked about Verilog syntax, and I also talked about structural Verilog. So here's an example where you have a structure where you have you instance a module, the AND3 module. We call it AND gate, and you have this section here that's the port map where you connect signals inside of my design to the inputs and the outputs of the AND3 module that we've instantiated there. And I mentioned that what happens is you have this renaming process where inside of my design, we have a signal declared as called N1. And that signal would be equivalent to the Y signal inside of AND3, right? So same signal, 2 different names, depending on where in the hierarchy you're looking at it. This was a similar example, except in this case, we have 2 modules instantiated, and then we create port maps between the signals in the NAND3 module and the modules that we've instantiated in there, which are the AND3 and the inverter. Okay, and then I mentioned you can have multi-bit signals. So in this case, we have a module called gates. We have 2 inputs, A and B, and they're both 4 inputs. And you have to watch out for this syntax because basically we're creating an array, except the array bounds are given before the names of the signals. So this is the type is logic 3 down to 0. And in this case, that type is being applied to both A and B, right? And when you simulate, you'll see the simulation looks a little different. If these are single bit signals, you'll have high and low. So each signal will have a green line that will either be low or high. It'll look like an oscilloscope. Whereas if you have multi-bit signals that you put in here, it looks more like a logic analyzer where you have lines on the top and the bottom. You see that? There's a line on the top and the bottom. And then anytime there's a change in the value, there's like an X. The top and the bottom lines cross. A little hard, I don't know if you can see that in the back, and also this image has been, I squeezed this a little bit. So this is a little bit out of proportion, but you have it'll show, the value in here, and then the changes are indicated with a cross. Okay. And then this is a mux, basically just an assigned statement with a ternary operator in there. And there's another example of a full adder. And then I talked about operators in SystemVerilog. I mentioned that this table is incomplete because there's a equals 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 and a bang equals equals, the two different ways to test for quality depending on if you're using them in code that's intended to be deployed in a design, synthesized, versus code that's in a test bench. Okay. I'll talk more about that when I get to test benches. And then I mentioned that whenever you have a number in Verilog, you should specify the bit width, followed by an apostrophe, the base, and the number. Now you're going to notice that even the textbook doesn't follow this rule all the time. I don't know why. And then if you look at the code that we give you as part of the lab skeleton, there are even cases in there where we don't follow this. But it's good practice to specify bit widths. You guys with me? So I'll point out, whenever that comes up. And then we have bit manipulation, also called bit twiddling. So you can do concatenation with the curly brace. You can rip out bit ranges with the brackets, and you can do duplication with double nested curly braces. Everyone okay with that? Okay. And then I also talked about Quartus. So let me do a quick demo just to show you what I mean by this. So when you download the lab skeleton, you're going to get a gzip tar file, in this case lab_hex.tar.gz, and then you can extract that and then go inside of the lab hex directory, and you'll see there's our script at the top, and then there's a QDF file, an HTM file, a QPF file, a QSF file, a QWS file, and an SDC file. These are all just part of the project, the Quartus project. Then there's the hex driver, SV, that's a design file. That's what you're supposed to fill in as part of Lab 2. So this is kind of an empty module. And there is a simtop.sv, which is the simulation top. That's the top level. When you simulate, you run the Testbench function of the script. And then there's top.sv. So you're going to have to modify all three of those files. Okay? And then there's a README, which is the lab sheet. And then there's this tar file in here, which I think is superfluous. Okay, so if you want to open this in Quartus, you can just run Quartus with an R. And you can you just do File, Open Project, and you can open that QPF, that's the project file. And once it's open, come on. Usually it doesn't take that long. There it is. You'll see here that we're targeting the Cyclone 4 FPGA. It's the one that's on the board. There's the top level module listed in there because this is the hierarchy view. Now, technically under top, there should be hex driver in there, right? So if I double click on top, there's the file. And is there a hex driver? No, actually not. There's not. We haven't instanced that for you. You're going to have to instance the hex driver. Okay, so that's why there's nothing listed in there. You can always go to. You can also go to the files. View, and you can see top.sv, hexdriver.sv. You won't see simtop because we're not synthesizing simtop. That's only for simulation. So Quartus doesn't need to know about simtop. SDC stands for Synopsys Design Constraints, and this is what tells, let's see, can I scale this a little bit better? There we go. That's no, probably not. This design constraints is telling Quartus that we're looking to achieve a clock period of 20 nanoseconds, which is 50 megahertz. So that's when it synthesizes the design, it has to guarantee that the chip will operate at that clock rate, even if you're operating it in your oven. It's doing a worst case analysis over different temperature ranges and different device variations. Okay. And then if you want to compile it, you can double click on the compiled. There's a design flow here. If I can, I'll just scroll down. If you compile it, it'll do the analysis and synthesis, and the assembler, timing analysis, EDA netlist writer. That's just all the steps it goes through to synthesize it. The other thing you can do is you can go to assignments and pin planner. This is kind of cool. So this is actually a picture of the underside of the FPGA. So the FPGA is a ball grid array, and it has 780 pins, I believe. So there's this grid of pins. I think in the middle, I think there's no pins right in the middle. I think there are pins are on the sort of the periphery, but there's still a bunch of them. And you can see a table where it's associating the names of the top level inputs and outputs to pin locations. So the clock 50 pin is pin Y12. So Y is the row and 12 is the column, I guess. All right, and then you can also see the I/O standard, current strength kind of stuff, I/O bank. So you can see right away why there's 3 clocks. So each of these clocks is a 50 megahertz clock. They're all the same, but they're placed in different I/O banks. We're just going to use clock 50. Hey, and yeah, so that's about it. You can if you took 313, you're probably familiar with this. You can program the FPGA here through Quartus if you want. However, we also have a script for you. So if you run the script, you can type CSCE 611 compile, and this will synthesize it in the command line for you. Now you'll notice it doesn't bring up the Quartus GUI, but it is running Quartus in tickle mode. And so if you have any errors from the compile, they'll be listed there, and then you can go fix them.
I got an error.
Yeah. Do you remember what it was?
It was, I wasn't allowed permission. It was a permission. But I think it's because I copied files over instead of doing the tar like we did. So maybe it was missing. So.
Okay, we'll have to look at that in lab because I don't know off the top of my head what could cause that. Okay, so you can see that it finished. It takes about a minute or so. And this is the reason why these FPGAs, because the other big FPGA vendor, AMD, their compile takes a lot longer. Also, you can run CSCE 611 Testbench, and this will run QuestaSim. And you'll notice, that, again, there's no GUI. It just runs it and prints out any error messages. Yes? QuestaSim? So QuestaSim is just for simulation, and Quartus is for deploying it deploying your design. So if you want to implement your design on the FPGA, you use Quartus. And if you want to simulate it, basically for debugging purposes, verification, use QuestaSim. Now, in this class, it is common for students to decide they don't want to ever use QuestaSim. They will do all their testing on the FPGA, which is pretty rough because it's hard to determine where the problems are if you just run on the FPGA. They do have a thing called signal tap where you can insert virtual logic analyzers inside the FPGA. You can put little scopes on signals, and then you can deploy the design on the FPGA, and you can actually monitor those signals as it's running on the FPGA over USB. It's pretty cool. The problem with that is that every time you want to add another probe, you have to recompile your design. So it's kind of cumbersome. And you can use that. Actually, that's really your only choice if your design works in simulation and doesn't work on the FPGA. How often does that happen? Not very often, but it can happen. So if everything checks out in Quartus, you put on the FPGA and you got a paperweight, then you're going to have to use chip scope. But we can help you out with that in the lab. I used to talk about it in lecture, but hardly anyone uses chip scope. Okay, let's take a look at the, while we're here, let's take a look at these files. So here's SymTop. So SymTop is deliberately made with no inputs and outputs. So it just says module SymTop semicolon. And there are local signals that are declared for each of the inputs and outputs into the top, right? And then we instance top, and it's called DUT, design under test. And so we're going to, in this case, we're not connecting the LED green and red. So there's nothing in the parentheses. We're only connecting the clock. So the clock is going to is an input into the design under test. So we have to drive the clock in SymTop. SymTop has to clock it, has to toggle the clock. I don't think we do that. Do we do that? I don't think we do that. No, you have to do that, right? So you're going to put your test code in there, right? So the only thing that's going on in here is we're instancing top for you. Anything else we want to do for testing, you have to put in. Okay, then we have top. Okay, so top has inputs and outputs that are deliberately set to match those from that table I showed you in the pin planner. So these have to match magic names that correspond to actual IOs on the FPGA. Any other module, you can have arbitrary IOs, but for the top level module for the FPGA, these have to match real actual IOs on the chip. So we have LED-G and LED-R. These are 9 bits of green and 18 bits of red LEDs. Those are, you can see those here. So I've got 18 reds and there's actually 8 greens here, and then there's a green up here in the middle of the hex displays. And then there's the hex displays, so there's 56 bits there because there's 8 hex displays and each one is 7 bits. Unfortunately, we don't have access to the decimal point. We just have the 7 segments. And then there's an input for switch. There's 18 switches, and then there's 4 keys, which are buttons. That's a horrible name for that. Why not button? Or push button. They call it key. But the keys, these are the keys, and these are the switches here. Right? So those are key and switch are inputs, and then 7 segment displays are outputs. Okay, then we have some code in here. What's this code? This code is kind of a little sanity check for you. It's a design that we put in, and let me show you what it does. So if we run the script and we say program, so CSCE 611.sh program, come on. I don't know if it's going to work. It worked just before I came down here, so let's try this. Let's hit that. Oh. Okay. Let me try to unplug, replug. Okay, and also, I know what to do. Kill all JTAG D. All right, let's try that again. Let's run JTAG config, and it sees it, but it's hung. Okay. Okay. Yeah. Let's try in Quartus, see what happens. If I open Quartus, and let's go to recent projects, open that up. And let's try kill JTAG D. Look for JTAG config. There we go. Now it's good. I think it'll work now. So I'm going to try the script. I'm going to do program. There we go. Now it's good. Okay, so when it's programming, you can see it stopped flashing the lights. Okay, so here's what you get when you program the design that we give you. You can see that there's an LED that's just kind of moving back and forth. Okay. So inside the design, the way that works is we have to create a clock divider because you can see that this thing's moving kind of slow. It moves about 1 LED per half second or so, right? And so you have to find a way to slow the 50 megahertz clock down to something that's this slow, right? So we use a clock divider, which is it's a 26-bit value, and I'll talk about initial statements here soon, but it's a 26-bit value that we increment once per cycle. And then we use the most significant bit of that counter as the clock, right? So for every bit you add to the clock divider, you're dividing the clock speed by 2, right? So if you have a 26-bit counter, you're dividing the clock by 2 to the 26th power, which is 32 million, right? So you're taking a 50 million cycle per second clock and you're dividing it by 32 million, which makes it, 1.4 hertz or something like that. I think that says on here somewhere in the comments. Okay. All right. So I'll get back to the syntax there in a minute. So, so if you program and it runs like this, you get a sanity check that you got a good board and you got a good connection. All right. So, so we talked about Quartus, and then I demoed Model Sim. Now, unfortunately, I can't directly simulate this design in Model Sim. I mean, I can, but it's not practical. Anyone know why? Yes?
It doesn't have all like the LEDs and switches and buttons? Or?
Yeah, that's part of it. Yeah, I would need a way, if I simulate this in Model Sim, I need a way to also simulate the inputs. Now in this case, this design doesn't require any inputs except for the clock, right? So I would need a way to stimulate the clock if I do it in simulation. There's another reason too why it's not really practical at the moment. The other reason is that the clock divider has to increment 32 million times before it's going to move the light one position. So if I simulated this, I would have to let it simulate long enough to get 32 million clock cycles for one thing to happen of importance, right? That would be a long simulation, right? Wouldn't really be practical. And that's the problem with designs like this, is that we've slowed them down to a time scale that's not really practical. Now, one thing we could do is we could separate the clock divider from the inner core, right? And then we could simulate just the inner core at just a faster clock, right? But our design isn't that nice. It's all mashed together, and the clock divider and the logic for moving the LED is all in one module, right? But this would be a good case where you'd want to have different modules, right? You guys follow that? Right? We could have an inner module that would simulate the light moving and the shifter, and then we could just simulate that with just every cycle, right? And then you could have an outer module that creates the clock divider. But because they're all together, it's a monolithic design. It's difficult to simulate. Okay, let's see.
I have another question about the FPGA and the Testbench.
Yes.
The switches drive the LED segment. If you're doing an automated test bench, can you overdrive that by forcing a signal?
Yeah, that's exactly what you want to do. Yep.
Okay. So
Yeah.
there's no error created by having two sources.
No, because in the top there's nothing driving the switches, because it's going to be driven by by the physical switches, right? And then in SimTop, right now there's nothing in SymTop that drives them either, but you could put that in. Yeah. Okay, so in lab 2, I went over all this stuff. So there's 3 files, SymTop, top, and tester, and I tried to draw, how everything fits together. And the hex driver. Oh, sorry. The tester. Actually, we didn't give you a file for the tester. This code would be, you could create a module for this tester, or you could just inline your test code inside the SymTop. Okay, so let's talk about that. Oh, first, before I talk about that, I got to talk about the always statement. Okay, so I've only given you so far one way to do behavioral logic in SystemVerilog, and that's through the assign statement. But really, the only thing you could do on the assignment statement is just create Boolean logic or maybe some adders. But the only kind of logic you can make with an assign statement is combinational logic, meaning that it's just a function of the inputs. You have an output that's a function of the input. So anytime any of the inputs change that are on the right-hand side of the assign statement, it triggers an update of the output value, right? What that means, though, is you can't create any memory. You can't create any sequential logic. Did you guys talk about sequential logic in 2.11? Do you remember that? You guys talk? Okay, good. Yeah, so sequential logic is when you have memory involved. That could be flip-flops or latches or RAM. Combinational logic doesn't have any kind of memory. Now, what is this design? Is this design combinational or sequential? This is sequential logic because when it moves the position of that LED, it's moving it as a function of what it was in the previous state. So it has to maintain memory to keep track of where the LED is, right? So this is a sequential logic design. When you guys do your lab 2, that's going to be combinational because you're just going to flip switches and the hex displays are going to update immediately, right? So you don't need any memory in the design you do for lab 2. Of course, when we get to the CPU, we're going to have to add memory in that one. That'll be sequential because we need to have an instruction RAM and pipeline registers and so forth, okay? Make sense? Okay, but how do we make sequential logic? We have to use this always statement. So an always statement is, it's a statement, but you can create multiple lines of code in there by using begin and end. Those are kind of like equivalent to curly braces in C or Java, right? Or using indents in Python. So an always statement allows you to create basically a more complex a more complex assign statement if you're doing combinational logic, but it also gives you the ability to make sequential logic. Okay? So in Verilog, the syntax was always followed by the sensitivity list, followed by the statement or block of code, right? However, the problem with that was that it created this common issue where you would write an always statement and you would intend to make combinational logic and it would make sequential logic because of the bug in your code, right? And so SystemVerilog introduced variations on the always statement so you can tell the compiler what your intention is. So you have this thing called always_comb, which is used for combinational logic. And if you use an always_comb, the sensitivity list, which is the list of signals whose change will trigger the always statement, is implied to be whatever signals you use as inputs in the always statement. So anything on the right-hand side of an assignment or anything that's part of a conditional. Okay? On the other hand, if your intention is to make a sequential logic, then use always_FF. FF standing for flip-flop, right? And then that you're followed by the sensitivity list, which generally for sequential logic is just the clock. In fact, it's usually an edge of the clock, because typically you do edge-triggered sequential logic. Does that make sense? Although if you want an asynchronous reset, you can put that in there, and I'll show you examples of that. Okay, so those are now you can always just say always. You can still just say always with the sensitivity list. You can use the Verilog syntax, because remember, SystemVerilog is a superset of Verilog. Okay, so let's look at an example here. So if you have a code that looks like this, where you say assign out equals, and then you just have a ternary statement, right? you could replace this with the equivalent version of this with an always, which would be always comb and then begin and end. Now in this case, the begin and end is actually optional because there's only one statement in here. It's the if statement. So you don't actually even need the begin and end. But, you know, in this case, they have it in there. And you could say, now here's where the syntax is a little different, because if you're in an always statement, you're allowed to use an if statement. You can't use it outside of an always statement. Why is that? I don't know. It's very strange choice they made, right? But that's the rules of Verilog. Same thing applies to VHDL too. Except in VHDL, instead of an always, they have something called a process, which is the equivalent mechanism in VHDL. Okay, so you say if select, then I'm going to set out1 equals foo, otherwise out1 equals bar. Okay, so in this case, foo, bar, and select are all considered inputs, right? Because they're all, well, they're treated like inputs in the code. So if any one of those three signals changes, it will trigger this always to update out1, which is the output. Likewise, this always now controls out1. So if you have another always that sets out1, then you're in trouble, because then you're double driving. So what I'm trying to say, and this is important, is that the always acts like an assign statement in that the always is a logic circuit. It becomes a circuit. And so anything you set in an always statement is controlled by that always statement. It's being driven, meaning that the always statement is either pulling that value up to VDD or pulling it down to ground, which means you can't have anything else doing that. Otherwise, you risk a contention. You guys with me? Yes, question?
So to use a multi-line conditional if statement, would you need to put ETA after that parentheses and line?
Yes, exactly. Yes. And by the way, that is really, you'll notice when you start doing that, it's awkward, especially if you have an if then else, because you have to type if condition begin statement, end, then else begin, right? So it becomes, it's a little cumbersome to have to spell out begin and end. But yeah, that's a good question. I didn't put the begin there because obviously there's just one statement, yeah, in the if and the else. Okay, so I just mentioned that. Okay, here's another example. Now here's one of the problems with always, is that what happens if the always activates because one of its inputs changes, but I don't set every possible output signal. Like, so in other words, remember that always is a circuit and it's driving everything that's assigned. You can have more than one output. So anything you assign in an always is an output. And the always is driving each of its outputs to VDD or ground, right? But what happens if I activate the always, but I don't set any of its outputs? So in this case, you'll see that I've got this default. So at the beginning of the always, I set out1 here. And then I have this if statement, which can potentially change what I want out1 to be, right? But if I didn't have this, line, if I just had the if, then the out1 would only be assigned if selected was 1. You guys with me? Right? What would happen then? Well, the always would then revert to becoming sequential logic because it would have to maintain the old value of out1. It would have to hold that in its memory. You guys, does that make sense? And actually, it would have memory but no clock. So that would make it a latch as opposed to a flip-flop. That's the kind of behavior you want to avoid. So whenever you use an always for combinational logic, you need to set the output, every possible output, regardless of the control flow through the always statement. Does that make sense? So that's the reason why I have this this default statement here, right? Or I could have had an else on this if statement. That would have been good too. The point is that I would be assigning the output regardless, right? You guys with me? Yes.
So when you create something sequential with some memory, is that, when you synthesize it, for example, does it actually create like a flip-flop or a latch or something?
Yeah.
Or does it use the memory for it?
Well, it uses, that's a good question. There are flip-flops on the board, on the chip, and it's going to allocate those. It's going to map one of those and use it. I've never actually tried to make a flip-flop though with like LUTs. Like you could create a LUT-based circuit that's cross-coupled and maybe create your own flip-flop. But no, there are hard transistorized flip-flops on there. Okay, well, what's going on here? What happens if select? By the way, here's an example where notice there's no size here specified. It just says if select equals 1. So this is the textbook, not writing very clean code, right? But what happens if, I think that came from the textbook. These slides are kind of a mixture of different sources. But what happens if select is 1? Is this out going to change? Or how does that work? Well, no, what happens is if you assign an output twice, inside and always, the only one that matters is the last one that gets assigned, right? You guys with me? Because remember, the goal is with with combinational logic, the goal is you're basically building a truth table here, but you're doing it in a more productive way than writing out a whole truth table. Okay. Does that make sense? Okay. All right, here's an example where I'm setting more than one output. That's pretty simple, just setting 5 outputs. Now here's the question, what's the point of using an always here? I could just use 5 assignment statements, right? Why use an always to do this? It's kind of inefficient. Yeah, it is. I mean, typically, I wouldn't use an always for this. I would use assigns. As a matter of fact, I try to always use assigns for combinational logic. The only time I would use an always for combinational logic is if you have a really complicated table, which is going to happen in this class when you build your control unit for your CPU. Your control unit is going to be a giant if-then-else sequence. And that would be, and not only is it giant because you have to have one entry per instruction, but in some cases it'll be nested because you'll see if it's a branch instruction, you'll go inside of one block, and then inside that block you'll check to see if the branch should be taken or not taken. So it's nested, it'll be a nested if statement. So in the case of your control unit, you'll use a big if then else, but that's probably the only time in this class you really need to use an always statement for combinational logic. You can use always, just an assign for everything else. Does that make sense?
Is there additional overhead then in synthesis when you use the always?
No,
Instead of just assign?
no, they're equivalent. Yeah, they're equivalent. So if you could use, an assign or an always to do like a mux, and they'll be equivalent. Okay, but the one time, here's another example where you might want to use this one. This is another exception too. So this is a 7-segment display, a 7-segment decoder, which is what your goal is to make in Lab 2. This is not complete though because you can't use this code for Lab 2 because first of all, it only covers digits 0 through 9. It doesn't include A through F, right? So you're missing some digits here. This is a base 10 7-segment decoder, right? We want to do a base 16 one in Lab 2. The other difference is that this one assumes that the segments are active high, where on the board they're active low, right? And I think the ordering of these is also reversed. So in the case of the board, it's the least significant bit is the top segment, right? And then so the bits go from right to left. In this case, they're left to right. But this is just an example of a way you could build a 7-segment decoder. And in this case, I'm now using a case statement. So you can use in addition to if statements, you can use case, although you'll notice the syntax is a little different than what you might be used to. And each one of these cases can also have begin and end as well if you want them to be multi-line. Make sense? But this is essentially equivalent to a switch statement in C or in Java. There's a variation too called a case Z where you can include don't cares in there as well. Right? Okay. Okay. So the more common use of an always is when you want to make sequential logic. You want to make memory. So here's an example of that where now I have, instead of always underscore comb, I'm going to use always underscore ff. And you have then you put an @ symbol, and then you can say pause edge clock. This means that this will activate on the rising edge of the clock. And notice here I'm using a different type of assignment statement. You see that it says less than equals instead of equals there? So when you make sequential logic, by convention, you should use this. This is called a non-blocking assignment. I'll talk more about that in a minute, but it's not equals, it's less than equals. It looks like a little arrow. This is something else that's unusual about this language. Okay, so this is saying on the positive edge of the clock, Q gets D, meaning that Q is going to stay the same value all the time, except for on the rising edge of the clock is when it will sample whatever D is and move it over to Q. Did you guys cover flip-flops in 211? Do you remember that? Okay. So this just creates a flip-flop. Notice I'm packaging this in a module called flop, which no one would ever do. Generally, you would just inline this code. So if you need a flip-flop in your design, you just put this code in your design. You probably wouldn't create a whole module for a flip-flop because that would you'd end up with a lot of very short modules. You guys with me? Okay. So here's another variation that includes a reset. So same idea, except there's another input called reset. Now notice though that reset is not in the sensitivity list, and neither is D for that matter, right? So the reason why this creates memory is because I don't have all my inputs in the sensitivity list. I just have clock. So that means that that's what tells the compiler, the synthesizer, that you're creating sequential logic, because I have outputs that are a function of inputs, but the inputs aren't in the sensitivity list, or at least not all of them. In this case, I just have clock in there. That make sense? So this creates a synchronous reset because I can reset this guy to 0, but only if I have reset high and I get a rising edge of the clock at the same time. Reset by itself will not reset this guy. I need a reset in combination with a clock edge, right? However, you can create an asynchronous version if you put pause edge reset inside the sensitivity list, which means this guy has the ability to reset even without the clock. It's an asynchronous reset. Now, which one should you use? Kind of usually doesn't matter. You can use either one. Right? So for example, your program counter in your CPU will be built this way. Your program counter needs a reset, obviously, because that's what that's how you reset your computer, right? You hit the reset, it sets the program counter to 0, and then it starts fetching instructions starting at address 0, which is your bootloader. But does it matter if that reset is synchronous or asynchronous? Are you probably not? No, right? Okay, and then here's another variation that has an enable. So this one has a third input called enable, where you can set the enable to 0, and then even if you get a clock edge, it'll ignore it. So this would be for something like if you have a register that you only want to enable, like for example in MIPS, we used to have the high and low registers that were only written if you did a multiply, if you execute a multiply instruction. You guys with me? So what is the point of all this? The point is that it's not like you're just taking flip-flops and using them like you did in 211. Now you have the ability to customize their behavior. In fact, you can do even crazier things, like for example, You can create, do I have it here? I don't have it. I guess I deleted it. You can create, you don't even have to have something where you have a D that goes into Q. You can make a counter here where instead of D here, you can say Q gets Q plus, or Q gets Q plus 1. Q gets, the new Q is going to be is an incremented version of the old Q, right? In which case you can create a counter. You don't even need a D input. Make sense? In fact, that's what we're doing on the FPGA. So we'll go back and revisit that code here in a second. Okay, so I'm going to, this part is confusing to the point where it's almost impossible to explain. But I mentioned that inside and always, you can have an equal sign to assign a signal, or you can use a less than equal. The equal sign is called a blocking assignment, and a less than equal sign is called a non-blocking assignment. The difference is that inside and always, I mentioned earlier that Verilog has concurrent semantics, meaning that the order of the lines of code don't matter. Right? You can take all the lines of code and you can scramble them. The exception to that is the code that's inside and always. Inside and always, the whole point of an always actually is to create a little island of code that has sequential semantics. Right? That's the reason why I was able to, for example, set out 1, I was able to give it a default output, and then right below it have an if statement that changes it potentially, right? That's a sequential semantics. Does that make sense? Right? Right. So let me clarify that. So if we go back to this example here, right? The order of these lines of code actually does matter, because if I were to swap these two lines of code, then out 1 would always get bar. It could never get foo, right? You guys with me? Okay, so there is some sequentiality within an always statement. However, it gets a little weirder, because if you have a dependency in terms of your assignments, so notice here I set N1 is going to get D, and then Q gets N1. You see there's a dependency there where the first line of code is setting a value that the second line of code uses as an input, right? The behavior of that will depend on whether you use blocking or non-blocking. If you use non-blocking assignment statements, then the second line of code is not going to see the new value of N1 that was established in the line above it. It's going to see the old value of N1, because in a non-blocking assignment, these assignments don't take effect until you've run the whole thing through, the whole always statement through. You guys with me? Does that make sense? So this is going to take the old D and put it into N1, and the old N1 and put it into Q, right? These guys, so what this will end up doing is creating a shift register, right? Where essentially Q will be whatever D was 2 cycles ago, because N1 is whatever D was 1 cycle ago, and Q is whatever N1 was 1 cycle ago. But that N1 is not updated until after everything finishes, the whole assignment statement finishes. Okay, so the convention is whenever you make a sequential logic, you should always use non-blocking assignments, right? Unless you explicitly intend for blocking behavior. Blocking behavior is when you intend for that second line of code to see the change from the first line of code. So I'm going to put D into N1, and then I'm going to use N1 and put it in Q. The problem is that this code actually doesn't do anything. This code actually just creates one flip-flop, right? Because the old D goes into N1, which is now equivalent to the old D, and then Q gets N1, which is the old D, so Q is just getting the old D from 1 cycle ago, right? So Q is imposing a 1 cycle delay on D. Whatever D was last cycle is what Q is now. So if I look at Q, it's like looking back in time 1 cycle at D, right? Whereas over here, I'm looking back in time 2 cycles because there's a 1 cycle delay that's imposed by each line of code, because I have to run this assignment statement once completely to update N1, and then run the whole thing completely in order to get that N1 back in the queue, right? So that's the difference. There are actually more implications, though, of blocking versus non-blocking as it relates to things going on in different always statements. That's where it gets really weird. This is just described in behavior of how these affect statements within one blocking. But what happens if I have these kind of data dependencies in across multiple always, right? So it gets complicated, but the best way to go is to just use the convention of less than equal to if you have memory, and just equal if you're making combinational logic. So in your control unit in your CPU, use equals, but in your flip-flops, in your register file, and any kind of memory, you use the less than equals. You guys with me? Okay. By the way, just to give you a point of reference, in VHDL they do the same thing, but it's a little bit more clear in VHDL. In VHDL, you have a signal versus a variable. And so if you want blocking behavior, you declare something as a variable. And if you want blocking behavior, you declare it as a signal. So in VHDL, this is implemented through the declarations of the thing that you're assigning. Whereas in Verilog, it's done through these operators, these assignment operators. Does that make sense? I like the way that VHDL does it a little bit better in that sense. It's a little bit more readable. Okay, this slide just says what I just said. Okay, so now let's talk about test benches. So I showed you, I think I did a demo last Monday where I used QuestaSim to simulate a design, and I used force statements in QuestaSim to set the inputs, and then I visually observed the corresponding output, right? But that's a really bad way to test. I mean, it's good for testing little things and doing debugging, but it's not a great approach for testing overall, right? Because you don't want to have to just stare at a waveform to figure out if your design is working. A better way to do it is with a test bench. And so the idea with test benches is that you write Verilog code that's designed to be run in the simulator, but never intended to be synthesized. And for that reason, Verilog has things that you can put in your code that are not synthesizable, right? Things that are intended just for simulation, like, for example, print, right? You can put a print statement in Verilog, and it'll print to the console when you simulate it, but obviously you can't print if it's on the FPGA, right? I mean, at least not directly from the hardware. You have to have a whole, serial console infrastructure to print something, right? Another big one is the delay operator. In Verilog, you can put hash sign 2 semicolon, and that will put a delay for 2 units of time. That's also not synthesizable. So if you have any non-synthesizable code and you try to synthesize it, you'll get an error because it's intended for simulation. But when you write a test bench, you're going to put a lot of non-synthesizable code in there because it's intended as a harness that's going to drive the inputs into your design under test, which is the thing that you're going to synthesize, and then it will check the outputs, and it will automatically check the correctness, and if they're incorrect, they'll print an error. Does that make sense? So, so here's an example. So here's a real simple module called silly function. Has 3 inputs, 1 output. It's just a Boolean function. If I want to test, now obviously I can synthesize this, but if I want to test it, I can create this test harness where I can use this thing called an initial statement, which is a block that just starts executing at the beginning of the simulation. And I'm going to use it to set inputs, set the A, B, and C inputs. And then after setting them, I'm going to use this delay operator. You see this hash 10, hash sign 10, pound sign 10? Whatever that thing's called, right? This will delay the simulation for 10 units. Why? Because remember I mentioned there's no delay when you simulate behavior, right? Because there's no underlying device technology that's being considered here. We're just testing the logic behavior. We don't have any kind of logic delay idea of how long it takes to propagate logic, how long it takes to charge and discharge the capacitors that create the logic. we're not simulating that. We're just simulating the behavior. However, there is a non-zero delay. So if you set inputs into a combinational logic function, the output will not change until you simulate for any non-zero amount of time, right? It has to be, it could be infinitely small, right? But it has to be a non-zero. So that's what these things are. I'm telling it to delay for 10 units. It doesn't have to be 10 units. It can be 1 unit of time, right? It could be an attosecond, right? It doesn't matter because we don't really care about how much delay, just the fact that there is delay. So you have to set the inputs and then have some kind of delay, which just, I'm using 10 as an arbitrary number. So I do hashtag #10, and then I set the other value in 10. So I put delays every time I change the input. Does that make sense? Now this is not checking the output because I'm assuming in this case I'm just going to look at the waveform, but at least I've got a stimulus, right? I'm setting the inputs. So this is going to go through all 8 permutations of A, B, and C, right? However, it would be better if we can check the output, so you can put code in there for that as well. So in this version, I set the inputs, and then I check Y with an if statement. So I set A, B, and C to 0, 0, 0, have it delay for 10 seconds, or 10, I guess, picoseconds or nanoseconds, whatever the simulator is set up to do. And then I check Y, and then if it doesn't match, I'm going to use $display and print a message, right? And then I'm just going to keep repeating that sequence. Does it make sense? Now notice I use bang equals, right? So this example came from the book, even though they did not put the bang equals in their operator table. Remember that? I had to point that out, right? But yeah, this is a special testing non-equality for non-synthesizable code, Testbench code, right? Why is that? Because in some cases you want to test for X or Z in here, which you're allowed to do with the bang equals, but not with the bang equals. Make sense?
You don't have clock in this one.
No, no, I don't use the clock. Now, I'm going to show an example where you do. You can use the clock for a test bench. In this one, everything is it's just based on this delay. But that's not, you may not want to do it that way. Another way to do, oh yeah, speaking of which, so you can use the clock is another way to do it. So if you have a clock, well, okay, let me clarify. So this is a combinational circuit, and I'm going to use a clock, even though clock is not part of combinational logic, but I'm going to use it just to run the test bench, right? If you have sequential logic as your design and your test, then obviously the clock matters, and you may have to write a test bench that, for example, waits for 5 clock cycles after the inputs, if that's the delay of that logic operation. Like if it's a 5-cycle operation, you may have to count cycles. You guys with me? So it can get a little complicated, but in this case, I'm going to use the clock in a way where I'm going to use the rising clock edge to assign the inputs, and then I'll use the falling clock edge to check the output, right? Why? Just because it gives me a non-zero amount of delay, right? And it's a convenient way to kind of to run everything, right? So, so another thing you can do is you can use test vectors. So instead of having to put all of the inputs and their corresponding expected outputs in if statements, right? I mean, well, in not assign statements and if statements. You can create a file with the inputs and expected outputs, and this is generally called test vector file. So in this case, I'm going to put the inputs 0, 0, 0, and then the output 1, right? So this is basically a truth table that defines the input-output for that circuit, and so I have an underscore here because Verilog ignores underscores in numbers. So that can just be used a way to separate the inputs from the outputs visually. Okay? So now the problem is that in order to make this work, I'm going to have 2 versions of the output. So there's one version of the inputs, A, B, and C. Then I have a Y that I'm expecting. That's my ground truth Y, right? The Y from the test bench. The test vectors. And then the actual Y that's coming out of my design under test. So I've got those declared here. I've got Y and y expected. And why those are in two different lines, I have no idea. They could have just been combined. You see it says logic ABC, y expected, logic y, right? I don't know why those are on two. Could have just put those all in one line with clock and reset too. Make sense? Okay, then I've got a 32-bit value for vector num and errors. It's going to keep track of what vector I'm on and how many errors I've found. So I'll put those in 32-bit. And then this is where things get a little crazy syntax-wise. So my test vectors are going to be put in a RAM. And a RAM is a two-dimensional array of bits. Right, where there's rows, which correspond to the addresses of the RAM, the entries, and the columns, which is the width of the RAM, how many bits I get out at a time. Okay, now in C, if you declare a two-dimensional array, what goes first? The rows, then the columns, right? So if I declare an array in C, and the first number I put in the array is 10, and the second number is 20, that's 10 rows, 20 columns, right? Same thing in linear algebra, like math uses that too. It's always rows and then columns whenever you have a two-dimensional array. In Verilog, they switch them. They're backwards. So the first number, 3:0, is the width, meaning the columns. There's 3 columns. And the second number, which is 10,000 down to 0, is the depth, number of rows. Why do they do it that way? I don't know. I think it's because, you know, by having logic 3 down to 0, it makes it consistent with the one-dimensional signals in there, right? And then when you make a two-dimensional signal, you put that after the name of the signal. Right? So it's 3 down to 0, test vectors 10,000 down to 0. So it's creating a 10,001 row RAM that's 4 bits wide, 4 bits across. You just have to get used to that. That's crazy, crazy, crazy syntax compared to other languages. Okay, then we have the design under test, which we just wire to A, B, C, and Y. Those are local signals. And then I have this little thing that will generate the clock signal. So this is something I'm going to have to put, you guys are going to have to put in your sim top, right? So basically it's just always, begin, and end. So this is a special form of the always that is non-synthesizable because there's no sensitivity list. If there's no sensitivity list, then it is a non-synthesizable always. Now you might say, wait a minute, always COM, it doesn't have a sensitivity list. Yeah, that's because it's an always COM. But if it's just an always with no sensitivity list, then this is something that just repeats infinitely. So if you put clock equals 1, pause for 5 units of time, clock equals 0, pause for 5 units of time, this will create a periodic clock signal in the simulation. But again, you can't synthesize that. You might say, well, wait a minute, then how does the clock work in the real hardware? The only way to do it that I know of is through a crystal oscillator, right? Or maybe you could do an oscillator with inverters connected in a ring. What was it? Ring oscillator. You could build a ring oscillator. But generally speaking, the real clock is generated through a crystal, right? But this is the virtual clock. And then I have this initial statement where I use the $readmemb. Now, what is these dollar sign functions are called? VPI functions? Verilog Programming Interface? I think that's what they're called. I forget. But they're basically functions that you can call from Verilog, right? Special functions. This one initializes the test vectors with the data in example.tv. That's the file with the test vectors. And notice it's readmem B, which is for binary. There's also a readmem H for if you want to put hex in there. So this is going to initialize the RAM. This is also how we're going to initialize your program memory in your CPU design. It just, we're going to put your code from RARs, your machine code from RARs, will get initialized in the instruction memory the same way, which means this is synthesizable, right? This is actually synthesizable code. You can initialize a RAM like this and put that in hardware, but only because it's an FPGA. And the mechanism by which that works is when you program the FPGA, it initializes the RAM during the programming process. I don't think you can do this on an ASIC. Guys with me? Okay, so this is going to initialize that, and then we're going to set vector num to 0, and we're going to reset to 1, add a 27 time unit delay, and then set reset to 0. So that'll just put a reset pulse at the beginning for 27 units. Why 27? I have no idea. That's the authors of the book decided on that. They just picked a weird amount of time a random amount of time to reset for. Make sense? Okay. Then we have another always statement here. Now notice this is all in one module. I'm adding how many initial statements did I have, by the way? Let's go back. There's an initial statement there. Oh, there's only one so far. So I've got the one always statement there. I've got the initial statement, and there's another always, but this one is sensitive to the positive edge of the clock. And this one just uses an assignment statement with this bit twiddling thing, where I can take test vectors, vector num, index that like an array, and put it into those 4 signals, A, B, and Y expected.
Where do you change vector num so that each positive edge get a different?
Vector num gets initialized here to 0, and I haven't incremented that yet. I'm going to do that on the falling edge of the clock. So the rising edge of the clock, I'll change A, B, and C. And then now I've got negative edge of the clock. On the falling edge of the clock, this is going to check to see if Y equals Y expected, and if not, it'll print an error message. And I'm still not incrementing the vector num. I do increment the error count, though, if there's an error. And then, oh, sorry, that wasn't done. This is just the beginning of the always statement. And then I do increment the vector num. This is the second page. And then check this out. I've got the equals thing here. So I check to see if the vector num is x. 4'bx. The x's that don't know. What that's doing is going to check to see when I get past the edge of my initialized vectors. This will check to see when I'm done. Because remember, I allocated 10,001 entries for test vectors. I only used 8 of them. So when I get to the 9th, I'll get an x, and then I know to stop. And then you've got this $finish. This will shut the simulator down, right? So when you type R script CSCE 611.sh testbench, it'll run until it hits a finish, right? If you don't have a finish, then that script will never stop. It'll go forever, right? You got to have that $finish. On the other hand, though, if you're running this in the GUI, then you got a problem because you get to that finish and it wants to shut the GUI down. So you have to hit, but it asks you if you want to exit, luckily. And are you guys with me? So in other words, this finish is great for command line simulation, but it's not so great for the GUI simulation if you do it in the GUI with the, with the waveform thing. Make sense? All right. That's all I've got.